So you might have heard the term semantic search before, but have you heard of vector search? They're very similar, if not the exact same thing. They really just mean, can we convert or encode really different types of data, videos, images, audio, documents, even time series data? Can we encode these data types into numbers? These numbers under the hood are embeddings. We get into what embeddings are in a previous video. And so once you have these types of data in embeddings, you can infer the semantic similarity between them. And so we've historically used similarity when we talk about keyword search. And in this, on the left-hand side, you have heart attack symptoms. And if we can see heart attack symptoms, the term, the phrase, we're looking for exact word similarities, heart attack symptoms, but it doesn't really understand synonyms or kind of similar words and really the intention behind the query. Right? And it also fails to understand domain specificity, right? So if you're working with healthcare data or legal data or even technical data, it doesn't understand these relationships between words. And this is really what you can understand as, does this word align with this word? And what we've evolved into is really allowing us to capture the concepts behind the words. So on the right-hand side, you have semantic search, which really is just meaning-based matching. Right? So heart attack symptoms, we can infer that it understands heart attack symptoms, chest pains, cardiac arrest, coronary syndrome. But what the prerequisite for this understanding is we need an encoder model, an embedding model that understands these relationships, understands these domains. And we do have very general purpose encoder models out there. OpenAI has published a fair bit, and there's quite a few on Hugging Face on the top leaderboard for embedding models, which we'll get into in a bit. And these different embedding models have various trade-offs for how accurate they are at some of these different concepts. And we call these precision and recall is how we measure the accuracy and the breadth of these retrieval systems. Right? So we have historically keyword search where we're just matching words. And then we've evolved into semantic search, really matching concepts and meaning and intention. Right? So under the hood, what is actually happening? Right, we have two very common vector similarity algorithms. There's a third here. So we have cosine similarity, we have dot product, and not pictured here is Euclidean distance. It's less so common for more general purpose use cases. But the very first concept here, the very first algorithm we can think of is cosine similarity. Right, and so again, we can encode anything into points. And once we have these points, we can map them on a plane. Right, so we have XY coordinates that we're very familiar with when we think about our high school geometry days, but we have X, Y, Z, and all the way up to 1,000 of these dimensions. And these multi-dimensional points can be plotted in multi-dimensional space, in latent space. Right, so when we compare king and queen, right, so we have king here, 0.5 and 0.7, and we have queen here, which is 0.3 and 0.9. The cosine similarity here in the proximity, the similarity score, is how close apart they are in this latent space, right? And so if we think about the actual cosine similarity, it really is just comparing, are these two vectors pointing in the same direction? Are they kind of going in the same direction in this plane? Right, and so this is very common for most systems that build semantic search. And then you have dot product. Dot product actually combines the direction with the strength of the vector and really how confident the signal of this vector is. So we have different examples here. King and queen, we can infer the similarity by measuring the distance. It's really just point A, point P, run it through a cosine similarity algorithm, and the result is the similarity score. Man, woman, king, man, queen, woman. They all have various similarity score metrics, results, but in the end of the day, they just are how we measure the semantic similarity between these points. Right, if you think about the actual architecture under the hood, okay, when a user issues a query, and this is how all chat systems work, right? And we'll get into what RAG is in a different video, but RAG, retrieval augmented generation, the R is really doing this. It's taking the query, right? When you're using a chatbot, you take this query, heart attack symptoms, you encode that query using an embedding model, in this case, text embedding 3 large. I think this is an OpenAI model. And maybe it's really good at a particular type of encoding. You have different specific domains of encoding models. You have healthcare specific encoding models, and you have general purpose encoding models, and even multimodal encoding models like CLIP. And so we take this heart attack symptoms query, we encode it using this embedding model. The result is an embedding, or it's a vector, and it has a fixed number of dimensions. Again, dimensions are just the number of points in that array, right? So going back to this example, we have 2 points here. That's the number of points in this king point. And so we convert heart attack symptoms into an array of embeddings, and then we run it through a cosine similarity algorithm. And typically we want to run it against an existing index of points. So we've maybe in the past already encoded those different terms. So in this case, maybe we've already encoded these phrases in our index. And this is typically stored in some kind of index data structure. HNSW, hierarchical navigable small world graphs, is a very common way to store these vectors, right? So let's say we've already ingested chest pain, we've already ingested cardiac arrest, we've already encoded these phrases. And so when we run this architecture, heart attack symptoms through the encoding model, get the resulting query vector, run that query vector through our HNSW, our index of existing phrases, then the documents that are returned are the most relevant, right? And so this is at its core how pretty much every RAG system operates. The very first step is some kind of semantic search or feature search, right? And so this allows you to do really intent-based retrieval. Cheap flights to New York City, we can understand the intention behind this query is we want to find affordable air travel options to New York City. And so we can actually expand the query into other types of documents under the hood, right? Maybe we've already captured all of these different budget airlines. Maybe we've already captured all of these tickets. And so we can infer this relationship because we've mapped the query vector, cheap flights to New York City, to all of the documents that have their own encoding. So we just find that similarity. Similarly, if you have kind of a how-to guide or people are looking for help, how to fix a leaky faucet, right? So then we find all of the components in maybe our documentation about tap repair that aligns to the different methods of repairing a leaky faucet. And so the sky's really the limit because really it's just a matter of what you can encode. Can we encode these phrases? And if we can encode these phrases, we can find the similarity, right? And so what does this look like in practice? How do we actually operationalize this? So this is Mixpeek University, Multimodal University. And so in our documentation, we actually have examples of really running feature search at scale, right? So if you think about feature search, what we just talked about, KNN, K nearest neighbor, we find the nearest neighbor of these points that we've already queried, right? So we can use text as an input, we can use image as an input, we can use video as an input to our query for the semantic search, for the KNN, for the vector search, right? And so again, we have the query input, we use some kind of encoding model, we can apply some kind of pre-filter saying, hey, I only want results that have these specific attributes. And this is really important because we want to actually limit the results before we do the most expensive operation in our retrieval system, which is very often the KNN. And there's some more advanced methods of combining different types of encoding. This is where a lot of the more sophisticated multimodal capabilities come in. You have reciprocal rank fusion, RRF. We've got learned weights, which is really just can we combine scores based off of interactions of users. This is how most recommendation systems work. We'll get into that in a later video. And then the ultimate result set is the documents. And the documents are what you're looking for. And they all have their own scores, etc. And so let's look at what an actual data set looks like. In this case, we've got a bunch of collections in our namespace. These collections, we'll just run through we'll do the scene segments collection. And all of these they're just videos. These videos have different start times, they have different end times, and they have all of this different text that was provided for this use case. And they also have embeddings. Right? And this is very important because these embeddings are what we're doing search for. And so for Mixpeek under the hood, we actually abstract the concept of embeddings so that you don't have to think about the different encoding models. You don't have to think about the dimensions. You don't have to think about anything. So you select the namespace, right? In this case, we have two encoding models in this feature extractor, this multimodal extractor V1. We also have a text extractor, and we are in this collection. We are just running the raw objects, in this case videos, through this feature extractor. And this feature extractor, in this case, let's see, we are just using the multimodal extractor v1. And so we can see, we get into in a different video what object decomposition is, but the source of this processing is some kind of video. We're running it through this scene segmentation collection. The scene segmentation is encoding it into a multimodal embedding. In this case, we're using a vertex multimodal embedding model, and I believe it is 1408 dimensions. So it all comes together. We're using cosine similarity, and it's a dense vector. And you have different types of vectors. You have sparse vectors. You have multi-vectors. You have lexical vectors, etc. Right. So now let's go ahead and create a retriever. So we'll call this test query, and we'll run it on a collection that we already have. In this case, the scene segments. Again, the scene segments using the multimodal vertex embedding. Similarly, like we just talked about, 1408 dimensions, cosine, etc. You don't have to think about any of that. You just think about what do you want to index and what do you want to retrieve, and then you build the retrieval pipelines. And so in this case, we'll just do a text query, but because our systems are multimodal, and as long as the actual underlying embedding model supports other modalities like text, image, video, audio, etc., we can use these as different types of queries. And this allows us to do not only text-based retrieval, but also image-based retrieval. Given this image, find similar image. Images. Given this video segment, find similar video segments. So we'll just call this query. And so this is the input schema for the retriever. And we've got our base result set. This just gives us the ability of experimenting live. And we have all of these different retriever stages in the platform. I believe we're at 24 right now. And all of these retriever stages, really what they do is they allow you to reconstruct your objects. So we were saying we were decomposing the objects. We can reconstruct them. We can enrich them using outside sources, databases, website lookups, API calls, or even other collections in our namespace. And so we can recompose them, we can enrich them, etc. And so in this case, we are doing a very basic semantic search, right? In this case, we call this feature search. We can name the stages. So we'll call this semantic search. And so this retrieval stage is really just saying, hey, use this feature URI. This feature URI is basically just an abstraction on top of the encoding model plus the vector index that we've already constructed because we've already ran our videos through that pipeline, right? And so we'll just put dog here. And so this is just giving us the ability of kind of simulating what that and really building out the retrieval pipeline. So we'll run that right here. And what this is really just saying is, again, use this feature URI. The input mode is text, and the actual variable, the value that we want to provide in this text input for this feature search, KNN search, semantic search, etc., is this value here. And then we have all of our results, and we have the score of each of them, right? And so these are all just values that are specific to this collection. But this is great because, okay, now we have the results from this feature search. We can limit the results to the top 5. This is important because if we are limiting the results, then it makes the operations a lot more affordable under the hood. Affordable really just means, is it speedy? Is it fast? Is it not? Is it computationally efficient? Right. So this is the feature search stage. We've got a bunch of different examples. We can do a single modal search here. What we just did. We can do image-based search. So we want to provide a reference image as the retrieval. There are tons of other options. So reciprocal rank fusion, we'll get into that in a different video, et cetera, et cetera. So this is feature search. We can combine the results we can send the results of this feature search stage to any number of other stages. We can use an LLM filter, which really just means given each of these results, apply some kind of LLM-based filter to each of the documents from the previous stage. And it does this in parallel, so it's efficient. And this one is really just saying, keep only documents tagged as GA releases, or we could say, just as an example, let's see, keep only documents that have relationship, keep only documents related to dogs, right? And so then we run this. When we run a stage here in the later pipeline, it also runs all of the previous stages. And so it actually reduced the results from the previous stage by 1, probably because maybe the LLM didn't think that it was relevant to this dog. We're using the Gemini 2.0 Flash model. etc. And so this is the retrieval pipeline builder, and we can see when we have the actual retriever, we can run different operations. So in this case, we have the retriever stages. We capture interactions. We've got performance metrics. We've got benchmarks associated with the actual semantic search or the retrieval pipeline. And we can also publish our retriever so other people can use it. And one final thing is once we have the points in semantic space, we can, going back to the example we showed you earlier, we can actually compare, okay, how is queen very similar to king? How is king very similar to man, etc. And so we can see this in using a clustering algorithm is what are some of these points similarities in this plane. And when we do clustering, we actually reduce the embeddings from, I believe the original collection was 1408 dimensions, and we're just reducing it to 2 dimensions. And this is what allows us to actually map it on this 2-dimensional plane here. And so we have these points. These points are all, again, mapped on this plane. We have XY coordinates, and we have clusters. These clusters have labels. They have summaries. These are automatically generated. But what's interesting is we can take one of these points and we can find similar points. We can do a reverse search of a document against other documents. So we'll get into all of this stuff in a later video. But at its core, really what we talked about here is building a semantic search stage in the retrieval pipeline. And so feature search is the stage in the retrieval pipeline that you use in order to build semantic search. And the sky's really the limit as far as what sort of capabilities you want to bake into your retrieval system. But yeah, so my name is Ethan, and I'm the founder and CEO of Mixpeek, and we are really just building a very flexible, a very robust, scalable system that allows you to do not only semantic search, but really all of the multimodal analytics and retrieval operations that you can do across your unstructured data. So your videos, images, audio, documents, and we've got tons of examples, got tons of use cases, templates, blueprints, recipes, etc., all on the website, mixpeek.com. Thanks.